17 October 1969, Saint-Laurent-des-Eaux nuclear power plant, Loire River, central France. In the control room of reactor A1, status boards show steady operation, 390 megawatts electric, carbon dioxide flowing at design pressure through 3,000 vertical channels of graphite and natural uranium. Above the core, a charging machine moves on rails, inserting fresh fuel without shutdown, a technical achievement of France's national reactor line. At 12 minutes past midnight, in-caisson radiation monitors record a count rate climbing above background. Operators expect routine refueling fluctuations. The trend does not pause. By 12:22, activity exceeds trip thresholds. Automatic systems scram the reactor. Power falls to zero. Gas circuit monitors confirm what the logs will later state. Fission products in the coolant, cladding failure, fuel damage. 5 elements, about 50 kilograms of uranium, have partially melted. France's first commercial power reactor core damage accident has begun. They do not yet know it will require a year to repair. 1st June 1969. Saint-Laurent-des-Eaux nuclear power plant begins commercial operation. Reactor A1 connects to the French grid, the latest unit in the uranium naturel graphite gas line developed by the Commissariat à l'énergie atomique and operated by Électricité de France. On engineering schematics, the concept appears elegant. Natural uranium metal fuel requires no enrichment. Graphite moderates the chain reaction. Pressurized carbon dioxide removes heat through vertical channels machined into stacked graphite blocks. Thermal output reaches 1,650 megawatts. Net electrical generation, 390 megawatts. The Loire River, 28 kilometers upstream from Blois and 30 kilometers downstream from Orléans, provides the ultimate heat sink for the secondary water steam circuit. The design serves dual purposes. Electricity generation supports France's industrial expansion in the 1960s. Plutonium production in the irradiated fuel supports the national weapons program. Both depend on using domestic natural uranium without importing enriched material from the United States or the Soviet Union. Charles de Gaulle's government favors gas-cooled reactors as a French solution, distinct from American pressurized water designs. By 1969, Électricité de France operates UNGG units at Chinon, Bugey, and now Saint-Laurent. Each demonstrates the technology's promise: online refueling without shutdown, fuel turnover synchronized with electricity demand, and independence from foreign fuel cycles. The Institut de Radioprotection et de Sûreté Nucléaire will later summarize the line's characteristics. 2 reactors of the uranium naturel graphite gas line were operated at Saint-Laurent-des-Eaux. Saint-Laurent A1, 390 megawatts electric, and Saint-Laurent A2, 450 megawatts electric. Fuel consists of natural uranium metal clad in magnesium zirconium alloy. Graphite sleeves surround each fuel element to maintain geometry and channel carbon dioxide flow. The gas, pressurized to approximately 30 times atmospheric pressure, flows upward through the channels, absorbing fission heat and transferring it to steam generators. Safety systems include automatic trip on high caisson activity, temperature monitors at channel outlets, and carbon dioxide pressure and flow indicators. The Service Central de Protection contre les rayonnements ionescents oversees environmental monitoring beyond the site boundary, measuring ambient dose rates and sampling river water, sediment, and air. External surveillance stations operate continuously, establishing baseline radioactivity from natural sources and weapons test fallout. Operators expect readings to remain stable during normal operation and refueling campaigns. Yet even as A1 reaches full power in mid-1969, Électricité de France's strategic direction shifts. Internal analyses favor pressurized water reactors for future construction based on capital costs, fuel cycle economics, and international standardization. The decision precedes the October accident, but will later be framed through it. UNGG represents French ingenuity and independence. PWR represents proven scale and lower unit costs. By the end of the decade, the choice is already made. Saint-Laurent A1 and A2 will be among the last gas graphite units built. The paradox is documented. 1969 begins with A1's commissioning as a flagship of national technology and ends with its core damaged, its future uncertain, and its design already sidelined in planning documents. The contrast between industrial ambition and operational reality will define the next year, early 1969. Above the reactor vessel of Saint-Laurent-des-Eaux, a charging machine travels on rails across the top biological shield. Weighing several tons, the device positions itself over vertical standpipes that access individual fuel channels. A computer program controls displacement, alignment, and component transfer. The machine maintains carbon dioxide containment during operations, sealing to each standpipe before opening the channel and withdrawing or inserting fuel elements, graphite sleeves, or flow control devices. Online refueling distinguishes UNGG technology from earlier reactor designs that required shutdown for fuel changes. The charging machine stores up to several dozen components in internal chambers, each indexed by the control program. A typical fuel channel operation involves removing spent elements, inserting fresh fuel, and adjusting graphite plugs or flow restrictors to fine-tune coolant distribution across the core. The program ensures that fuel goes into fuel channels, graphite components into graphite positions, and flow control devices into designated locations. Position tables track what sits in each chamber and what belongs in each channel. The system includes protective interlocks. If the program detects an inconsistency, a component in the wrong chamber, a command that would mix incompatible parts, the machine halts. The stop is automatic, triggered by logic that compares the programmed sequence against the machine's internal inventory. Designers expect these stops to be rare, indicating either a data entry error or a minor fault in the tracking system. However, the machine also permits manual override. Operators can bypass the automatic stop and resume the sequence using manual controls. The interface provides no direct visual confirmation of what actually sits in a chamber or in the target channel below. Identification depends entirely on accurate bookkeeping, on the assumption that the component loaded into a given chamber is the component the system believes is there. If the internal record diverges from physical reality, manual override converts a protective stop into a pathway for error. The Institut de Radioprotection et de Sûreté Nucléaire later describes the charging machine's role in the 1969 accident. A flow control device was introduced into a fuel channel during a fuel loading sequence, greatly reducing cooling of the fuel elements. The flow control device, an organe de réglage de débit in French technical terminology, is a graphite plug designed to constrict carbon dioxide flow in channels where cooling demand is lower. Inserted into a fueled channel, it throttles coolant flow below the minimum required to remove fission heat. Post-accident investigation reveals the sequence. The charging machine stops as designed, detecting an inconsistency before inserting the flow restrictor. The operator, believing the stop indicates a benign fault, uses manual control to complete the operation. The restrictor enters the channel. Coolant flow drops. Fuel temperature rises. The protective logic functions correctly. Human judgment overrides it. The documented lesson is clear. Automation can prevent errors only if its warnings are heeded. The charging machine's interlocks represent one layer of defense. The decision to override them represents a failure of another layer, operational discipline, and the understanding that automatic stops in nuclear systems warrant investigation, not dismissal. 17. October 1969, shortly after midnight. Saint-Laurent-des-Eaux operates at nominal power. Core thermal output matches design expectations. Carbon dioxide inlet and outlet temperatures lie within normal bands. System pressure holds steady near 30 bar. An online refueling campaign is in progress on the night shift, one of dozens conducted since commissioning. Operators monitor global parameters, total reactor power, average coolant temperature, flow rates through heat exchangers, while the charging machine executes its programmed sequence above the core. Operating philosophy assumes that online refueling can proceed without perturbing reactor stability. Fuel turnover occurs in small increments, with fresh natural uranium elements replacing spent fuel one channel at a time. Reactivity changes are minor and controlled by adjusting control rods. Any significant anomaly, loss of coolant flow, unexpected power increase, cladding failure, should appear in global indicators. A power surge, a temperature spike, a pressure transient. The instrumentation suite provides continuous trending. Operators expect to detect problems before they escalate. Reality diverges from this assumption. The most critical event on 17 October occurs inside a single vertical channel, one of 3,000. Global power remains stable. Total carbon dioxide flow through the core changes negligibly. Average outlet temperature does not spike. The problem manifests locally. In one channel, coolant flow drops to roughly 1/4 of design, but the reactor's overall hydraulic resistance barely shifts. Pumps continue circulating gas at near normal rates. Power distribution across the core remains within expected variation. The accident is invisible to global trending until fission products leak into the coolant. The instrumentation that matters is radiological, not thermal or hydraulic. In-caisson radiation monitors sample gas activity continuously, detecting isotopes that should not be present during normal operation. These monitors are sensitive to xenon, krypton, iodine, and aerosols, fission products that escape only if cladding fails. During startup, shutdown, or routine refueling, activity levels remain near background, reflecting trace contamination from prior operations or minor surface deposits on fuel. A sustained rise above baseline indicates cladding breach. The Institut de Protection contre les rayonnements ionisants maintains external monitoring stations around the plant. Ambient dose rate instruments and air samplers operate continuously, establishing the radiological background from natural sources and residual weapons test fallout. Environmental measurements provide the second layer of protection, ensuring that any release beyond the reactor building is detected and quantified. These measurements will later show no anomaly from the October accident, confirming that containment functioned as designed. Precedents exist for graphite gas reactor accidents involving local cooling failure. Windscale in 1957 experienced a graphite fire after air cooling proved insufficient. Lucens in Switzerland suffered fuel melting in January 1969, 9 months before Saint-Laurent's event. Both demonstrated that gas-cooled reactors are vulnerable to channel-level blockages that do not immediately register in global parameters. Électricité de France and the Commissariat à l'énergie atomique are aware of these cases. The knowledge has not yet translated into instrumentation or procedural changes that would catch a single block channel before damage occurs. At 12 minutes past midnight on 17 October, the night shift at Saint-Laurent A1 monitors a reactor that appears entirely stable. Core power is steady. Coolant parameters lie within limits. The refueling program is on schedule. No alarms sound, no indicators suggest trouble. Yet in one channel, magnesium zirconium cladding is already beginning to overheat. 17 October 1969, early morning hours. The charging machine halts mid-sequence. The programmed logic detects a mismatch between the commanded operation and the component identified in one of the machine's storage chambers. An interlock engages. The sequence stops. A warning indicator illuminates on the control panel. The system is designed to prevent exactly this situation, loading the wrong component into a channel or mixing incompatible parts within the machine's handling path. The operator monitoring the refueling sequence interprets the stop as a minor fault, perhaps a data entry error in the position table, or a sensor glitch in the chamber identification system. Charging machine stops are not unprecedented. Some reflect genuine inconsistencies that require investigation. Others result from conservative logic that flags ambiguous conditions as errors. Distinguishing between the two often requires judgment. The schedule calls for completing the refueling campaign on time. Delays mean reduced availability, lost generation, economic penalty. The operator decides to override the automatic stop. Manual controls allow the sequence to resume. The machine aligns with the target channel, seals to the standpipe, opens the access port, and inserts the component in the chamber. The operation completes. The machine moves to the next position. The interlock, once bypassed, does not re-engage. The refueling program continues. Post-accident investigation reconstructs what happened. The chamber held a flow control device, a graphite plug designed to constrict carbon dioxide in channels needing less cooling, instead of the fuel element the program expected. When the operator overrode the stop, the machine inserted the restrictor into a channel already containing fuel. The plug lodged at the top of the channel, directly above the fuel stack. Carbon dioxide flow dropped sharply. The Oak Ridge National Laboratory's summary of the event states, "A coolant flow restrictor, rather than a fuel element, was in position to be loaded, reducing coolant flow in that channel to about 1/4 of its design value." The geometry is simple. Natural uranium fuel elements sit vertically in the graphite channel. Carbon dioxide flows upward around the fuel, absorbing fission heat. The flow restrictor, placed at the channel inlet, throttles the gas. Less coolant means less heat removal. Fission power continues at the same local rate, set by neutron flux and fuel enrichment. Cladding temperature climbs. In a single channel, the balance between heat generation and heat removal shifts decisively toward failure. The global core parameters barely respond. One restricted channel out of 3,000 adds negligible hydraulic resistance to the total circuit. Pumps maintain system pressure and flow with minimal adjustment. Reactor power does not change. Coolant outlet temperature, averaged across the entire core, remains stable. The event is invisible to operators watching the main control board. Only when fission products enter the gas will instrumentation detect the problem. The Institut de Radioprotection et de Sûreté Nucléaire's later analysis underscores the causal chain. The charging machine, commanded by a programmable displacement system, stopped during the operation. This stop was then overridden, allowing the introduction of the flow control device into the fueled channel. The protective interlock did its job. The human decision to bypass it converted a detected inconsistency into an unmitigated hazard. The documented fact is stark. The machine warned, the operator overrode, and 5 fuel elements began to melt. No single failure caused the accident. The combination of design, allowing manual override without direct visual confirmation, and procedure, treating automatic stops as obstacles to schedule, created the pathway to core damage. 17 October 1969, minutes after the misload. Inside the blocked channel, physics dictates the outcome. Fresh natural uranium fuel elements continue fissioning at the power level commanded by reactor control systems. Neutron flux, control rod position, and coolant temperature set the local fission rate. Nothing in the core's neutronics changes when the flow restrictor enters the channel. The fuel continues generating heat at design intensity. Only the cooling has changed. Carbon dioxide flow drops to approximately 1/4 of design. Heat removal falls proportionally. Cladding temperature begins to rise. Magnesium-zirconium alloy, chosen for its neutron transparency and corrosion resistance in carbon dioxide, has well-defined temperature limits. Below 600 degrees Celsius, the alloy maintains structural integrity. Above 700 degrees, it softens. Above 800 degrees, it deforms and begins to melt. The fuel inside, natural uranium metal, has a melting point near 1100 degrees Celsius. The Institut de Radioprotection et de Sûreté Nucléaire describes the thermal progression. The temperature of the magnesium and zirconium alloy cladding of 5 fuel elements increased, causing their deterioration. Cladding does not fail instantaneously. First, metal creeps and bulges under internal gas pressure from fission products. Then, weak points crack. Fissures open. Fission products, noble gases like xenon and krypton, volatile iodines and aerosol particles, escape into the carbon dioxide coolant. The gas, now contaminated, circulates through the primary circuit, carrying activity, to monitors in the reactor caisson. 5 fuel elements, representing about 50 kilograms of uranium, experience cladding failure. The fuel had been loaded only shortly before the incident, so its burn-up is very low. This limits the inventory of short-lived isotopes available for release. Iodine-131, with an 8-day half-life, has not accumulated to the levels present in fully irradiated fuel. Cesium-137 and strontium-90, long-lived fission products, are present only in trace quantities. The radiological consequences, while serious, are less severe than they would be if heavily burned fuel had melted. Molten cladding and softened uranium metal sag within the channel. Some material flows downward onto the diagrid at the bottom of the core. The Oak Ridge National Laboratory notes that debris collects in the poubelle, a French term meaning trash can, referring to the collection space beneath each channel. This material will later complicate recovery operations, as it is no longer in a geometry amenable to standard handling tools. The core's total power output does not spike. Reactor protection systems do not trip on high neutron flux or high temperature. The accident lacks the dramatic signatures of a reactivity excursion or loss of coolant event. No sudden pressure rise, no steam release, no evacuation alarms. The event is confined to a single channel, invisible to global trending. Only the radiological monitors detect it. In-caisson gas activity climbs. Xenon and krypton, chemically inert, remain in the gas phase. Iodine, chemically reactive, plates out on surfaces or remains suspended as aerosol. Particulate fission products, trapped in the gas stream, circulate through the primary loop. Activity levels rise steadily, crossing the first threshold, then the second. At some point, the rate of increase exceeds the trip set point. Automatic systems initiate reactor shutdown. The physics is straightforward: reduced flow, elevated cladding temperature, material failure, fission product release. The sequence is deterministic. Once the flow restrictor entered the channel and the reactor remained at power, the outcome was certain. The only variable was time. How many minutes until cladding breached? How many more until activity reached trip level? The documented contrast is clear. No global power spike, no coolant system rupture, no containment challenge, yet 5 fuel elements damaged, tens of grams of fission products released into the primary circuit, and the reactor forced into an unscheduled, prolonged shutdown. Local events, global consequences. 17 October 1969, 12:22. In-caisson radiation monitors exceed trip thresholds. Automatic systems initiate reactor shutdown. Control rods insert into the core. Neutron flux collapses. Fission power drops to near zero within seconds. Decay heat from short-lived fission products continues, declining exponentially. Carbon dioxide pumps keep running, circulating coolant, to remove residual heat. The reactor is stable in the safety sense, controlled, cooled, contained, but contaminated. Gas activity monitors confirm fission products in the primary circuit. Xenon-133, krypton-85, iodine-131, and particulates register on instruments designed to remain near background during normal operation. The levels are unambiguous. Cladding has failed. Fuel has released its inventory. The question now is how much and where. External measurements tell a different story. The Service Central de Protection contre les rayonnements ionisants operates monitoring stations around the plant's perimeter and along the Loire River. Ambient dose rate instruments continue to record background levels consistent with natural radiation and residual weapons test fallout. Air samplers detect no increase in airborne radioactivity. River water samples show no anomaly. The Institut de Radioprotection et de Sûreté Nucléaire will later state, measurements carried out in the environment did not show any anomaly in ambient radioactivity levels. Containment has functioned. The reactor building, designed to confine releases during accidents, prevents fission products from reaching the environment. Ventilation systems, filters, and pressure control maintain the barrier between the contaminated primary circuit and the outside atmosphere. The public remains unaffected. No evacuation orders are issued. No protective actions are required. Off-site doses remain indistinguishable from background. Inside the reactor building, however, contamination is significant. Gas circulating through the primary loop carries fission products to every surface the coolant touches: heat exchangers, ducting, pumps, valves, instrumentation lines. Some isotopes plate out on metal surfaces. Others remain suspended in the gas. Dose rates near the damaged channel and in high activity zones of the circuit climb to levels that constrain human access. Recovery will require remote handling, shielding, and strict dose management. The Institut de Radioprotection et de Sûreté Nucléaire documents the immediate assessment. 5 fuel elements, representing around 50 kilograms of uranium, have undergone partial melting. Later recovery operations will retrieve 47 kilograms, confirming the scale of damage. The lost mass, approximately 3 kilograms, includes cladding, structural material, and small quantities of fuel that either vaporized or dispersed as fine particles within the circuit. The Authority for Nuclear Safety's historical review later classifies the event at level 4 on the International Nuclear Event Scale, an accident with local consequences involving significant damage to the reactor or radiological barriers, but without major off-site impact. The classification is retrospective. In 1969, INS does not yet exist. At the time, Électricité de France reports a serious incident with core damage but no environmental release. The terminology matters. Incident suggests operational difficulty. Accident implies a breakdown of safety functions. The distinction shapes public perception, regulatory response, and corporate accountability. The documented numbers provide scale: 50 kilograms of uranium melted, 47 kilograms recovered, 5 fuel elements out of thousands, 1 channel out of 3,000. Yet the consequences, year-long shutdown, complex decontamination, procedural overhaul, affect the entire reactor and eventually influence national nuclear policy. The contrast defines the event: technically contained, operationally severe, no off-site doses, yet internal contamination requiring months of remote handling, global parameters stable, yet local failure total. The accident did not breach the final barrier to the environment, but it breached multiple layers of defense in depth. Containment held. Everything inside it did not. 27 October 1969. 10 days after the accident, decay heat has subsided. Short-lived isotopes have diminished. Électricité de France begins recovery operations. The task is straightforward in concept: remove damaged fuel, decontaminate the primary circuit, repair or replace affected components, verify system integrity, and prepare for restart. Execution is constrained by dose. The Institut de Radioprotection et de Sûreté Nucléaire described the working conditions. Clean-up operations began about 10 days after the event. They were conducted largely using remotely operated tools. The operator's presence time above the core support area could not exceed about 10 minutes per operator. 10 minutes, not 10-minute intervals with breaks. 10 minutes total exposure time in the highest dose zones. Every action must be rehearsed, optimized, and executed with precision. Électricité de France constructs a full-scale mock-up of the damaged reactor region. Technicians practice on non-radioactive replicas, refining tool paths, identifying interferences, memorizing steps. Each operation is timed. Tasks are divided into subtasks, each assigned to a different worker to distribute dose. Supervisors choreograph entries like surgical procedures. Approach, perform, withdraw, hand off to the next team. No wasted motion, no improvisation. Remote handling dominates the recovery. Tele-operated tools, guided by cameras and manipulators, reach the damaged channel and surrounding structures. Debris is collected in shielded containers. Graphite sleeves are extracted. Contaminated surfaces are brushed, vacuumed, or chemically treated to reduce activity. Filters capture dust. Ventilation systems route contaminated air through high-efficiency, particulate filters before discharge. Dose rates vary by location. Near the damaged channel, radiation fields exceed levels compatible with extended human presence. In adjacent areas, dose rates allow brief entries for tasks requiring manual dexterity or visual inspection. Further from the hay, core conditions permit longer work periods. The spatial gradient of contamination dictates the recovery strategy. Remote tools for the hottest zones, short human entries for intermediate areas, normal access for peripheral work. 47 kilograms of uranium are ultimately recovered. The 3 kilograms not accounted for include vaporized material, fine particles deposited throughout the circuit, and residues too dispersed to collect efficiently. The recovered fuel is transferred to shielded casks and moved to interim storage, eventually destined for reprocessing to recover plutonium and unused uranium. The Institut de Radioprotection et de Sûreté Nucléaire notes a gap in the historical record. There are no detailed data available on the effluents generated during decontamination operations or on the collective doses received by workers. 1969 predates modern requirements for comprehensive dose documentation and effluent accounting. Records exist: logbooks, dosimetry badges, discharge reports, but systematic compilation and public disclosure are not yet standard practice. The absence of data does not mean absence of consequences. It means that quantifying those consequences decades later is difficult or impossible. Recovery operations extend through 1970. Modifications to the charging machine are implemented. Interlocks are strengthened. Procedures for handling automatic stops are rewritten. Manual overrides require additional authorization and verification. Position table accuracy is cross-checked with independent systems. The Oak Ridge National Laboratory summarizes the changes. The charging machine is made no longer so simple to override. 16 October 1970, 1 year and 1 day after the accident, Saint-Laurent-des-Eaux returns to service. Startup tests confirm system performance. The reactor reaches criticality, then power. Coolant parameters stabilize. Gas activity monitors remain at background. The core, -1 damaged channel, operates as designed. The accident is over. The lessons are embedded in hardware, procedures, and institutional memory. 1970 through 1979. Saint-Laurent-des-Eaux operates following its October 1970 restart. Refueling campaigns proceed under revised procedures. The charging machine's enhanced interlocks prevent repeating the October 1969 error. Gas activity monitors remain sensitive to any indication of cladding failure. External environmental surveillance continues, with routine sampling of air, water and sediment along the Loire. The Service Central de Protection contre les rayonnements ionisants publishes monthly bulletins summarizing radiological monitoring across France. Reports from the Loire Valley show ambient dose rates and radionuclide concentrations consistent with background and residual weapons test fallout. No persistent signal from the October 1969 accident appears in environmental data. The release was contained within the reactor building. Fission products that escaped the fuel did not escape the plant. Internationally, the 1960s and 70s see a broader learning curve for nuclear technology. The United States experiences fuel handling accidents at research reactors and fuel fabrication plants. The Soviet Union experiences larger-scale events in military facilities, some not disclosed for decades. Switzerland's Lucens reactor melts fuel in January 1969, 9 months before Saint-Laurent. The United Kingdom's Magnox reactors, also gas-cooled, accumulate operational data that inform design improvements. Each event contributes to the evolving understanding of how reactors fail and how failures can be prevented. Within France, Électricité de France consolidates its strategic decision to standardize on pressurized water reactors. The company had already announced this direction before the October 1969 accident, citing economic and industrial considerations. UNGG reactors require complex fuel handling, graphite maintenance, and gas circuit management. PWRs offer simpler operation, higher power density, and compatibility with international supply chains for enriched uranium and fuel fabrication. The 1969 accident does not cause the shift, but it reinforces it internally. The Authority for Nuclear Safety's historical review later explains, shortly after the 1969 accident, GCR technology was abandoned in favor of PWRs, although EDF had already chosen the PWR for economic reasons. The phrasing is careful. The accident is a factor, not the sole cause. Yet in public discourse and institutional memory, the connection between Saint-Laurent's troubles and France's move away from gas graphite becomes inseparable. By the late 1970s, UNGG units at Chinon, Bouguer, and Saint-Laurent represent legacy technology. New construction focuses exclusively on pressurized water reactors based on Westinghouse designs adapted by Framatome. The fleet expands rapidly. France commits to nuclear power as the foundation of its electrical generation, aiming for energy independence following the 1973 oil crisis. PWRs, not UNGG, will deliver that vision. Environmental monitoring data from this period show plutonium in Loire sediments at levels consistent with global fallout from atmospheric weapons tests conducted by nuclear powers through the 1950s and early 1960s. Later studies conducted in the 1980s and 90s confirm this baseline. Any contribution from Saint-Laurent's 1969 accident is indistinguishable from background by the time systematic sediment coring begins. The Authority for Nuclear Safety's retrospective classification assigns the 1969 event an INS level of 4, accident with local consequences. The same classification will later apply to Saint-Laurent's 1980 event. The authority describes both as the most serious nuclear events ever recorded in France, a statement that underscores their significance despite the absence of off-site health effects. The classification reflects damage to the reactor core, breach of radiological barriers within the plant, and the complexity of recovery, not environmental releases or public doses. The paradox is documented. By the time A1 restarts in 1970, its technology is already being phased out. By the time systematic environmental studies examine Loire sediments, the 1969 releases are no longer discernible. The accident shaped internal decisions and safety culture, but left minimal physical trace outside the reactor building. The contrast between operational impact and environmental footprint defines Saint-Laurent's first core damage event. 13 March 1980, Saint-Laurent A2, the second UNGG reactor at the site, operates at power. The unit, rated at 450 megawatts electric, has been in service since August 1971. Like A1, it uses natural uranium fuel, graphite moderation, and pressurized carbon dioxide cooling. Lessons from the October 1969 accident have been incorporated. Enhanced charging machine interlocks, stricter refueling procedures, improved operator training. The expectation is that these changes have significantly reduced the risk of coolant blockage during fuel handling. At midday, in-caisson radiation monitors register a rapid rise in gas activity. The trend is unmistakable. Automatic protection systems initiate reactor trip, control rods insert, power falls to zero. Carbon dioxide circulation continues, removing decay heat. Operators confirm the shutdown and begin assessing the cause. Gas activity levels indicate cladding failure and fuel damage. The signature is similar to October 1969, but more severe. Électricité de France mobilizes engineering teams. By 14 March, analyses confirm that a significant quantity of irradiated uranium has melted. The fuel involved is not fresh. It has been in the core long enough to accumulate substantial fission product inventory. The radiological consequences are correspondingly greater than in 1969. Xenon, krypton, iodine, cesium, and other isotopes are present in quantities reflecting months or years of irradiation. Inspections over the following 2 weeks identify the root cause. A corroded metal plate, part of the shrouding used for pressure measurement in the gas circuit, has detached and lodged across 6 vertical fuel channels. The blockage is partial in some channels, nearly complete in others. Carbon dioxide flow drops sharply in the affected regions. Local fuel temperatures exceed safe limits. Cladding fails. Uranium metal softens and melts. The Institut de Radioprotection et de Sûreté Nucléaire documents the damage. 2 fuel elements, representing approximately 20 kilograms of uranium, fully melted. 2 additional elements suffered significant partial melting. Molten material flowed downward into the collection space, the poubelle, at the bottom of each channel. The Authority for Nuclear Safety later confirms the event's classification as INES Level 4, matching the 1969 accident. The documented cause is different from 1969. No charging machine error, no operator override. Instead, a latent material failure, corrosion of a structural component over years of operation, creates a blockage that the reactor's instrumentation does not immediately detect. The plate detaches, moves through the gas circuit, and comes to rest across multiple channels. The blockage is not total, so global coolant flow does not drop enough to trigger low-flow alarms. Local temperatures rise without global indication until fission products leak into the gas. The contrast with 1969 is instructive. The first accident resulted from a procedural and human factors failure, an interlock overridden, a component misidentified. The second results from material degradation, corrosion undetected, a plate that should have remained secured. Both demonstrate the same fundamental vulnerability of gas-cooled reactors, sensitivity to local coolant blockages that do not register in plant-level instrumentation until radiological alarms trip. Reactor A2 remains at roughly 30 bar pressure, with contaminated carbon dioxide filling the caisson. The gas contains noble gases, iodines and particulates from the melted fuel. Operators face a dilemma. Decay heat is declining, but the reactor cannot remain pressurized indefinitely. Maintenance and inspection require atmospheric pressure inside the caisson. Depressurization means venting contaminated gas. Venting means releases to the environment, even with filtration. Électricité de France, the Service Central de Protection contre les rayonnements ionisants, and regulatory authorities begin planning a controlled discharge. Iodine traps and particulate filters are tested. Release pathways are verified. Meteorological conditions are assessed. The goal is to vent the caisson gradually over several days, minimizing instantaneous release rates and allowing decay to reduce activity levels. The operation will proceed in late March after the most short-lived isotopes have diminished. 22 through 26 March 1980. 9 days after the accident, Électricité de France initiates controlled depressurization of the A2 reactor caisson. Professor Pierre Pellerin, head of the Service Central de Protection contre les rayonnements ionisants, has briefed the plant surveillance committee. The reactor's primary circuit holds carbon dioxide at approximately 30 times atmospheric pressure. Restoring normal pressure requires venting gas through filters to the atmosphere. The discharge is planned, not accidental. Operators monitor meteorological conditions, wind, direction, stability class, precipitation forecast to optimize dispersion. Iodine traps designed to capture volatile iodine isotopes are placed in the vent pathway. Particulate filters remove aerosols. Noble gases, chemically inert xenon and krypton, pass through filters unchanged. The venting proceeds in stages over 4 days, allowing pressure to decrease gradually while maintaining control over release rates. Électricité de France estimates the total atmospheric discharge: 29.6 terabecquerels of noble gases and 0.37 gigabecquerels of iodine and aerosols. The Institut de Radioprotection et de Sûreté Nucléaire later confirms these figures. For context, 1 terabecquerel equals 1 trillion becquerels, or approximately 27 curies. 1 gigabecquerel equals 1 billion becquerels, or approximately 0.03 curies. The noble gas release totals roughly 800 curies. The iodine and aerosol release totals roughly 0.01 curie. The plant's discharge authorization in 1980 specifies annual limits: 296 terabecquerels per year for noble gases, 7.4 gigabecquerels per year for iodine and aerosols. Weekly limits are set at 44.4 terabecquerels for noble gases and 0.55 gigabecquerels for iodine and aerosols. The March 1980 venting releases 29.6 terabecquerels of noble gases, below the weekly cap, and 0.37 gigabecquerels of iodine, also below the weekly cap. The reported discharges fall within authorized limits. The Service Central de Protection contre les rayonnements ionisants issues its monthly bulletin for March 1980. The text notes, "Abnormal release of a small quantity of radioelements in a plant." The phrasing is restrained. Abnormal acknowledges that the release was unplanned, resulting from accident rather than routine operation. Small quantity reflects the comparison to authorized annual limits. The bulletin does not specify which plant or elaborate on the accident's cause. Public information remains minimal. Environmental monitoring data from the period show no detectable increase in ambient radioactivity beyond the plant's immediate vicinity. Air samplers and dose rate instruments operated by the Service Central de Protection contre les rayonnements ionisants record values consistent with background. The release, while measurable and reportable, does not produce off-site doses exceeding regulatory limits or natural variation. Decades later, the 1980 venting becomes a focal point of public debate. Activist groups and parliamentary inquiries question whether the releases were lawful, whether the public was adequately informed, and whether environmental monitoring was sufficient. The Institut de Radioprotection et de Sûreté Nucléaire and the Authority for Nuclear Safety reiterate that discharges were within authorized limits and that no deterministic health effects have been attributed to the event. The debate centers not on radiological safety per se, but on transparency, risk communication, and the adequacy of 1980s-era disclosure practices. The documented paradox is this. By regulatory standards of 1980, the venting complied with discharge authorizations and produced no measurable harm. By contemporary expectations of transparency, the minimal public communication and the delay in acknowledging a core damage accident appear inadequate. The numbers, 29.6 terabecquerels of noble gases, 0.37 gigabecquerels of iodine, are factually reported. The meaning of those numbers and the judgment of whether they represent acceptable risk remains contested. 21 April 1980. 5 weeks after the core damage accident, a separate incident occurs at Saint-Laurent-des-Eaux. A container holding a non-tight fuel element ruptures in the spent fuel pool. Contaminated water from the pool requires treatment before discharge. The treatment process results in liquid effluents containing alpha-emitting radionuclides, primarily plutonium isotopes, being released to the Loire River. The Institut de Radioprotection et de Sûreté Nucléaire documents the release. Approximately 1 gigabecquerel of alpha emitters discharged during cleanup of the contaminated pool water. 1 gigabecquerel equals 1 billion disintegrations per second. For plutonium-239, with a specific activity of about 2.3 gigabecquerels per gram, 1 gigabecquerel corresponds to roughly 0.4 grams of material. The quantity is radiologically significant but physically minute. Effluent management protocols in 1980 do not anticipate substantial alpha releases from power reactors. Discharge pathways are designed for beta-gamma emitters like cesium-137, strontium-90, and cobalt-60. Alpha emitters, plutonium, americium, curium, are expected to remain contained within fuel cladding or be captured during fuel handling and storage. The April 1980 release reflects an unanticipated failure mode, a spent fuel element not maintaining containment, contaminating pool water beyond the capacity of on-site filtration to fully capture transuranic isotopes. The Loire River, downstream of Saint-Laurent, carries the discharge toward the Atlantic. Dilution is rapid. Water monitoring stations operated by the Service Central de Protection contre les rayonnements ionisants sample river water at intervals. Plutonium concentrations return to baseline within days. Sediment, however, provides a more persistent record. Fine particles settle on the riverbed, trapping radionuclides and recording their deposition over time. Studies conducted in the late 1980s and early 1990s examine Loire sediment cores. Researchers measure plutonium isotopes, Pu-238, Pu-239, Pu-240, at various depths, corresponding to different years of deposition. A key diagnostic is the ratio of Pu-238 to Pu-239 plus Pu-240. Weapons test fallout, dominant globally, has a ratio near 0.03. Reactor-derived plutonium, reflecting different neutron exposure, has a higher ratio, typically 0.3 or above. Sediment layers corresponding to 1980 show elevated plutonium with isotopic ratios consistent with reactor origin. The magnitude matches the estimated release from April 1980. However, by the mid-1990s, cores from both upstream and downstream of Saint-Laurent show plutonium levels and isotopic ratios dominated by weapons test fallout. The 1980 signal, once detectable, fades into background. The Institut de Radioprotection et de Sûreté Nucléaire's 2003 radioecological assessment confirms this finding. Plutonium levels in Loire sediments upstream and downstream of Saint-Laurent are comparable and consistent with global fallout. No persistent contribution from the 1980 accident is discernible. The statement reflects decades of sedimentation, mixing, and decay. The original deposition remains in archived cores but is no longer distinguishable in contemporary environmental samples. Reactor A2 remains shut down for 2 years and 9 months following the March 1980 accident. Decontamination operations extend into 1982. The damaged fuel channels are cleaned using remotely operated tools. Uranium dust, dispersed throughout the reactor building, is vacuumed and filtered. Contaminated components are removed and packaged as radioactive waste. Several tons of lead shielding are installed to reduce dose rates in high-activity zones, allowing workers brief access for tasks requiring manual dexterity. Approximately 500 Électricité de France employees and contractors participate in the recovery. Dose management is strict. Collective dose is tracked, though detailed records are not publicly available. The recovery is more complex than 1969's, reflecting the greater fuel inventory involved and the added challenge of the pool contamination incident. October 1983. Saint-Laurent-des-Eaux restarts after 3.5 years of shutdown and repair. Startup testing confirms system integrity. The reactor reaches criticality, then full power. Gas activity remains at background. Coolant parameters stabilize. The unit operates for another 9 years before permanent shutdown in June 1992. By then, France's nuclear fleet is fully standardized on pressurized water reactors. UNGG technology, once the flagship of national independence, is history. Saint-Laurent A1 and A2, sites of France's 2 most serious civil nuclear accidents, enter decommissioning programs. The lessons remain embedded in safety culture, training, and regulatory practice. The environmental footprint, measurable in sediment cores and discharge records, fades into statistical background. 1970 through 1992. Électricité de France operates its UNGG fleet while constructing a new generation of pressurized water reactors. The strategic decision predates Saint-Laurent's accidents, but is reinforced by them. 9 gas-graphite units enter service between 1956 and 1972, 3 at Chinon, 4 at Bugey, and 2 at Saint-Laurent. All will be shut down by 1994, replaced by PWRs offering higher capacity factors, simpler fuel cycles, and lower operating costs. The decision reflects multiple factors. UNGG reactors require natural uranium fuel, which avoids enrichment costs, but yields lower burnup and requires more frequent refueling. Graphite moderators need periodic inspection and maintenance. Carbon dioxide coolant, while chemically stable, requires high pressure and presents unique handling challenges. Online refueling, initially promoted as an efficiency advantage, proves operationally complex and, as Saint-Laurent demonstrates, vulnerable to specific failure modes. Pressurized water reactors, by contrast, use enriched uranium, achieving higher burnup and longer fuel cycles. Water coolant simplifies heat removal and provides inherent safety characteristics, negative temperature coefficients, predictable phase transitions, and compatibility with passive cooling systems. PWR fuel assemblies are loaded and unloaded during scheduled outages, eliminating the need for online handling machinery. The technology is mature, with decades of operational experience from the United States Navy and commercial plants worldwide. Charles de Gaulle's government had favored gas-cooled reactors as distinctly French, independent of American or Soviet designs. By the early 1970s, pragmatism overtakes nationalism. Électricité de France, responsible for grid reliability and cost-effective generation, selects PWRs based on economic analysis. The International Panel on Fissile Materials summarizes the shift. France built 9 UNGG units, then chose pressurized water reactor types as standard, supported by domestic enrichment capacity and Framatome's manufacturing scale. The 1969 and 1980 accidents at Saint-Laurent do not cause this transition, but shape how it is remembered. Internally, the accidents inform safety assessments, design reviews, and regulatory expectations. Externally, they become emblematic of UNGG's limitations. The Authority for Nuclear Safety's historical volume states that, shortly after the 1969 accident, GCR technology was abandoned in favor of PWRs, even as the volume acknowledges that economic considerations drove the decision independently. Saint-Laurent A1 shuts down permanently in April 1990. A2 follows in June 1992. By then, France operates 54 PWR units with a combined capacity exceeding 58 gigawatts electric. The UNGG line is fully retired. Decommissioning programs begin. Fuel is removed, processed, or stored. Graphite moderators are segmented and placed in interim storage, awaiting final disposal pathways for long-lived, low-level waste. Primary circuits are decontaminated, cut, and packaged. The documented record shows no deaths, no acute radiation injuries, and no deterministic health effects from Saint-Laurent's accidents. Environmental releases remained within authorized limits. Off-site doses did not exceed regulatory thresholds or natural background variation. Yet the accidents are classified as INS Level 4, the most serious civil nuclear events in France, because of core damage, barrier breaches within the plant, and the extended recovery efforts they necessitated. The Authority for Nuclear Safety characterizes both accidents as formative in the evolution of French nuclear safety culture. Lessons learned include enhanced human factors engineering, stricter material surveillance and aging management, improved instrumentation for local phenomena, and more comprehensive environmental monitoring. The accidents prompted changes in operator training, procedural rigor, and regulatory oversight that extend beyond UNGG technology to the broader fleet. The paradox is complete. UNGG reactors, built to assert technological independence, are abandoned in favor of a reactor line based on American designs. The accidents that mark their final years left minimal environmental trace but maximum institutional impact. The contrast between physical consequences and policy consequences defines Saint-Laurent's legacy. 1993 through 2024. Saint-Laurent A1 and A2 enter the decommissioning phase of their life cycle. Électricité de France manages the process under oversight from the Authority for Nuclear Safety and technical support from the Institut de Radioprotection et de Sûreté Nucléaire. The work proceeds in stages: fuel removal, system decontamination, component dismantling, waste conditioning, site remediation. Fuel has been removed and transferred to Le Hague reprocessing facility. Spent natural uranium elements are dissolved, and plutonium and residual uranium are separated for potential reuse. Fission products and minor actinides are vitrified in glass matrices for long-term storage. The fuel that melted in 1969 and 1980 has long since been processed. Its isotopes are distributed, some decayed to stable daughters, others contained in high-level waste, others diluted into effluents within authorized limits decades ago. Graphite presents a unique challenge. Thousands of tons of moderator blocks, graphite sleeves and structural graphite remain in the cores. Neutron irradiation has activated impurities, creating carbon-14 and other long-lived isotopes. The material is classified as long-lived, low-level waste. France has no operating disposal facility for this category. Interim storage is the current solution. At Saint-Laurent, graphite is segmented, packaged and placed in concrete silos on site, awaiting eventual transfer to a deep geological repository under development. Decommissioning contractors use remote tools to cut and remove under-caisson circuits. Dose rates in some areas remain elevated decades after shutdown, requiring shielding and robotic systems. Contaminated components are size-reduced, sorted by waste category, and packaged for disposal. Very low-level waste goes to surface facilities. Low-level waste goes to Andres Centre de l'Aube. Intermediate and high-level waste awaits the CIGEO Deep Repository, currently in licensing. The Institut de Radioprotection et de Sûreté Nucléaire published periodic environmental radioactivity reports. The 2015 through 2017 assessment examines Loire River sediments, water and biota near Saint-Laurent. Plutonium concentrations upstream and downstream of the plant are statistically indistinguishable. Isotopic ratios match weapons test fallout signatures. No residual contribution from the 1980 accident is discernible in contemporary samples. The report concludes that current radiological conditions reflect natural background and global fallout, not operational or accidental discharges. This finding closes a decades-long debate. In the 1980s and 90s, detection of reactor-origin plutonium in sediments prompted questions about discharge practices and regulatory oversight. Some observers claimed illegal releases. Prosecutors opened inquiries. The Institut de Radioprotection et de Sûreté Nucléaire responded with systematic studies showing that detected plutonium was consistent with authorized discharges and that environmental levels posed no health risk. By the 2010s, the isotopic signature has faded. The conclusion stands: authorized discharges, no persistent environmental impact, no attributed health effects. The Authority for Nuclear Safety's historical volume, published as part of its documentation of French nuclear safety evolution, includes chapters on Saint-Laurent. The 1969 and 1980 accidents are described as the most serious nuclear events ever recorded in France. The phrasing is precise. Most serious reflects INS classification and institutional assessment. Ever recorded acknowledges that earlier events at military or research facilities may not be fully documented. In France, scopes the comparison to national civil and military programs, excluding foreign accidents. The assessment continues. The accidents played a major role in the evolution of nuclear safety and radiation protection approaches in France. The role is institutional, not radiological. No lives lost, no deterministic health effects, no long-term environmental contamination above background. Yet the accidents reshaped operating procedures, regulatory expectations, transparency standards, and public engagement. They demonstrated that containment can succeed even when multiple defense layers fail. They showed that local events in complex systems can remain invisible to global indicators until too late. They proved that technology choices have consequences, measured not only in performance metrics, but in resilience to unanticipated failure modes. Saint-Laurent's graphite sleeve silos stand as physical markers: concrete, steel, and irradiated carbon, awaiting final disposition. Inside, the material that moderated neutrons for 2 decades now waits decades more for a repository. The silos are monuments in function if not intent, reminders that nuclear technology operates on timescales exceeding human careers, corporate life cycles, and political mandates. The fuel melted in minutes, the cleanup took years, the waste will remain for millennia. The final documented fact is this: by the mid-2020s, environmental measurements confirm no ongoing radiological impact from Saint-Laurent's accidents. Sediments, water, air, and biota show concentrations indistinguishable from background. The reactors that experience France's most serious civil nuclear events have left no detectable trace in the environment they once threatened. The contrast between historical significance and environmental legacy is total. The accidents mattered enormously for what they taught, not for what they released.